So let the relation be an equivalence relation. On a set A. Then the distinct equivalence classes of the equivalence relation form a partition of the set A. And conversely, given a partition of the set A, there is an equivalence relation that has the sets in the partition as equivalence classes. Okay, so we'll prove the statement. So let the set of equivalence classes A sub I, or A sub I and some in the set A, be the collection of distinct equivalence classes of the relation. Then, as the intersection of any two is not empty, if and only if they are exactly the same, we have this from the previous theorem. As this statement is true, we have that A sub I intersected with A sub j is empty for distinct equivalence classes. And so the collection contains mutually disjoint equivalence classes. And as the union of these classes is the entire set A, this collection is a partition of the set A by definition. So again, we have a collection of non-empty sets. Each equivalence class of a given element contains at least that element, and so it's not empty. So if we take the collection of all distinct equivalence classes of the equivalence relation, then the union of all those classes spans the collection, or spans the set A. That is, the union is the set A, and each of these are mutually disjoint, as any two distinct equivalence classes will be empty, as the intersection of two distinct equivalence classes will be empty. And again, this comes from the previous theorem that it's only non-empty in the case that the two are exactly the same set. All right? So we'll look at the converse. So conversely, let the collection A sub I for I and some index set I be a partition of the set A. Then define two elements to be equivalent if and only if both are in the same subset in the partition. Then the set A sub I can be defined to be the set of all elements x in the set A, such that x is equivalent to x sub I, any one given element. That is, A sub I is an equivalence class which is distinct from the set A sub j, since the two sets are disjoint. Oops, is empty. Intersection is empty. So, given a partition, the natural equivalence relation is that the sets, or rather the elements in each set, be equivalent, in which case the sets are equivalence classes that are distinct from the other sets in the collection, since the any two of the sets in the partition are disjoint. Okay, so we're ready to look at congruence. Let the integer n be a positive integer greater than or equal to 2. And we will define a relation on the set of integers by A is related to B if and only if n divides A minus B. Then the relation is an equivalence relation. And if A is related to B, we say that A is congruent to B modulo n. So we'll show that this is an equivalence relation. So notice that the integer n does divide 0, which is A minus A. So we have the reflexive property. Suppose that A is related to B. Then the integer n divides A minus B, which means that A minus B is some multiple of the integer n for k some integer. And so B minus A is a multiple of negative k times n, which is an integer multiple. And so n divides B minus A, or in other words, B is related to A. So we have the property of symmetry. Okay, third, suppose that A is related to B and B is related to C. Then n divides A minus B and n divides B minus C. So n will divide any linear combination of A minus B and B minus C. Notice that A minus B plus B minus C is A minus C. Again, n divides any linear combination of the two, so n divides this, which is the same as a minus c. So a is related to c, so the transitive property holds as well. So the relation that we call congruence modulo n is an equivalence relation. And so in the language of an equivalence relation, we can state the properties of an equivalence relation using the notation for congruence. First, we have the property of the reflexive property. So A is congruent to itself mod n. 2, if A is congruent to B mod n, then B is congruent to A mod n. And the third property, transitivity, if A is congruent to B mod n and B is congruent to C mod n, then A is congruent to C mod n. So notice that the equivalence classes that contain a given element A, by definition, is the set of all elements x in the set of integers, such that x is related to A. And given this particular congruence or particular equivalence relation, that being congruence, this means that for every element x in the set of integers, the integer n divides x minus A. And so this is the set of all elements x in the set of integers, such that x minus A is some integer multiple of n. So this is the set of all elements x in the set of integers, such that x is A plus n times k for some integer k. And so we can rewrite this to be the set of all A plus or minus n times k, such that k is either a positive integer or 0. So notice in particular that the equivalence class containing the number 0, the integer 0, is the set of all multiples of the integer n. Once again, k is either a positive integer or 0. And we denote this as the integer multiples of the multiple n of the integers. So n times the set of integers. So notice that in particular this is the set of all integers that are divisible by n. Now, by the division algorithm, there are exactly or precisely n distinct equivalence classes mod n determined by the possible remainders upon division by n. namely the equivalence class containing 0, the equivalence class containing 1, and so on and so forth, up to the equivalence class containing n minus 1. And so the set consisting of these equivalence classes, these distinct equivalence classes, is a partition of the integers. Okay, so next we'll prove a theorem. Let A be congruent to B mod n, and let C be congruent to D mod n. Then A plus or minus C is congruent to B plus or minus D mod n. And 2, the product of A and C is congruent to the product of B and D mod n. Okay, so we'll prove this theorem. Since A is congruent to B mod n, we have that n divides A minus B, and since C is congruent to D mod n, we have that n divides C minus D. So n will divide any linear combination of A minus B and C minus D. So in particular, n will divide the difference of the two, A minus B and C minus D. Or in other words, n will divide A minus C minus B minus D. That is, A minus C is congruent to B minus D mod n. Also, n will divide the sum of the two, A minus B plus C minus D. Or rearranging this, we have that n divides A plus C minus B plus D. And that is, A plus C is congruent to B plus D mod n. And so we have that if A is congruent to B mod n and C is congruent to D mod n, then we have A plus or minus C is congruent to B plus or minus D mod n. Okay, so now we'll look at the product. Notice that AC minus BD is a linear combination of the two differences, A minus B and C minus D. In particular, it's C times A minus B plus B times C minus D. We have A times C minus BC plus BC minus BD. So this is a linear combination of the two. And as n divides A minus B and C minus D, it divides any linear combination. So n does divide AC minus BD. And so this is another way to say that A times C is congruent to B times D mod N. All right? So we'll define a new term. A set of n integers, which we'll label a sub 1, a sub 2, and so on, up to a sub n, are called, or the set is called, a complete residue system. Mod n if every integer is congruent to exactly one of the elements in the set. So exactly one of the a sub I.